So tonight we're going to be talking in greater depth about component families and building your own families and making the process more predictable, and talking about a strategy or strategies for building different kinds of geometries in your families. Now, most of the time, one of the most common, I guess, kinds of families that people need to build for their projects is a window. If you folks go into the Session 6 folder on the Share Out drive for tonight, I'm looking at the 313 light window. And this is the window that you see on the first page of tonight's notes. Now we're going to be talking about what the family editor, or what Revit calls constraints. Now, a lot of things about Revit are pretty user-friendly compared to other software platforms. Families, not so much. They are an uglier thing to deal with. So we're going to talk about some of the problems that you run into in the process. So first of all, this idea of a constraint. So if we look at this 313 light window, the way it works with our windows and doors is that when we start a new family and we use, say, the window template or the door template, we are presented with, in the elevation view, so here's the elevation view of a window template. We're presented with some reference planes that represent the sides, top, and bottom of an opening. The idea is that the first bit of geometry will be built at the perimeter. So going from left to right on the screenshots on the first page of our notes, we build from the outside in. So families are, of course, heavily reliant upon reference planes to make the behavior of the family work. So as families have their dimensions changed, their width, their height changed, that pushes the reference planes apart, and that's what makes your family change its size. So we're starting from the outside and working our way in. So when we look at the outside elevation of this 313 window, our opening is right there. You can see the blue line on the screen. That's the opening. And the first thing that gets built in this case is the exterior window frame. So that window frame is built and it's tied to the opening. So as the opening changes its shape, so goes the exterior window frame. Next, after the window frame's been built, if you put your cursor on the edge of the frame and hit the tab key once, that is the glass in the window. So the glass, it's fixed glass. It's not part of a vent in the window. So that's the second screenshot in the first page of the Session 6 notes. Then we have the frame for our vent, and that's the third screenshot. Finally, inside the vent, there is, of course, the glass inside the vent, which I got to by hovering over the inside edge of my vent frame and hitting the tab key once, so that the glass highlights in the vent frame and I can select it. So let's look at a little bit more detail at how this is built, starting with the outside frame. This is really similar to what you would have been taught in the intro course when we made that window. In that case, we had a frame around the outside, and then we had interior frames as well, and so we do here. So all these pink sketch lines are being controlled by dimensions, labeled dimensions in each place to drive the width of our window frame. So once that's done, when we come to put in the glass, and you folks, if you tab select and look at the glass extrusion, when you look at the extrusion sketch, you will see that there's no dimensions in here at all. And that's because each one of these pink sketch lines of the glass was put in place using the pick tool. So inside the glass extrusion, you hit the pick tool and lock's enabled. And so when the glass was being created, I just picked each of the inside edges of my window frame, which was already there in the background. And the glass now just moves around with the frame. So same thing with our vent over here. The only thing, of course, is that our vent frame does have dimensions inside it, so that if we want to change the width of the frame for our vent, you could do so. And then once that's done, we look at the glass inside, and of course there's no dimensions here either. As the vent frame changes size, the glass moves along with it. So this is a very clean approach, but you have to be disciplined. You have to build the glass inside the frame, and then you have to build the vent frame inside the frame, and then the vent glass inside the vent frame. So there's a structured manner with which this is built. Now there's another different approach, and it's the same family, but it's built with a lot more reference planes. So you'll see that the same family is provided in the Session 6 folder. It's just got ref planes appended to the file name. And when you look at it, the first thing that you'll notice is that there are, hold on here. So here's them side by side here. I'll just tile them. Now clearly one's got a lot more sort of dimensions visible. And so what I've done is that with this example here, all of the geometry in this particular example is tied back to reference planes that were drawn even before I built any of the extrusions for the frame or the fixed glass or the vent frame. And you can see the vent frame has reference planes for all of its bits and pieces as well. So this means that before I built the frame, and before I built the glass, and before I built the vent frame, and before I built the glass for the vent frame, those reference planes were in place like you see on my screen. So when I went to build these, let me just go back to the tabbed mode here. When I went back to building these geometries, when I look at these geometries and what's inside them, there are no dimensions, because the sketch lines that you see here are locked back to the reference planes that were already there before I started building this extrusion. So what's the real difference? Well, they both behave exactly the same way. One just has more reference planes in it, and you folks can decide which approach is better. What's nice about this one is that everything, the glass, the frame, the vent glass, you're always just using the pick tool when you are placing these sketch lines into place. You're just using the pick tool. You don't have to worry about putting dimensions on it, because all that stuff has already been done prior to the creation of those extrusions. So in some respects, this is an even more disciplined way of building a family. It's just that it's a little bit busier, and you have to do a little bit more work up front with creating all these reference planes. A lot of the families that you get from Autodesk are built with this method. And it's fine, I don't have a problem with it. It's just a little bit graphically, visually, and if you're trying to troubleshoot it and figure out what's supposed to snap to what, it can be a little harder to troubleshoot. But both ways are perfectly acceptable for building a family. Now let's go over to the second page here. We're going to talk some more about these constraints. So the constraints are things that we've seen already. So in the context of building geometries, whether it's a sketch line in an extrusion or a sweep path, but you all folks have used this where you use the align command or you use the pick tool with lock enabled. That's a constraint. So this edge of the opening here, when I use the pick tool and I lock it to that edge of the opening, that's called a constraint. So this pink sketch line for my window frame is constrained to the edge of the window. Now, here I've got one of the pink sketch lines on the inside of the window that has a dimension on it that keeps this pink line 2 inches away from the outside of the window because this dimension is sitting here. So that these other 2 sketch lines stay aligned with this one that has the dimension on it, rather than having to put this same dimension here and here. So that if the value of the frame width parameter changes, I want all 3 of these sketch lines to move because I want my frame everywhere to stretch. So if I use the align command, I can align my, using this first sketch line that's got a dimension on it, to another one here and lock them together. So by locking these 2 sketch lines, by constraining them to this one on the left that has a dimension on it, I know for sure that when this parameter changes its value to say 3 inches or 1.5 inches or what have you, all of these 3 lines are going to move together at once. So that's a constraint. Anytime you lock and align things together, that's a constraint. So there's different kinds of constraints. This is an edge constraint. And constraints can be, like looking at the 3 bullet points there, you can constrain these pink sketch lines to other geometry. Now the example of that is when I had my glass. So these sketch lines in the glass are constrained to the window frame, just as the vent frame over here, its outer edges are constrained to the vent frame. Now, the second bullet point there is constraining lines in a sketch to reference planes contained inside the sketch. Now, this is a sort of an interesting hybrid of that other family that I showed you earlier, the one that has the extra reference planes in it. In this example, the reference planes are outside of the sketch, right? So all these reference planes that you folks can see here, they're there before the extrusion is created. But what you can also do is you can put those reference planes inside your sketch. And you'll see here now that these reference planes that I'm drawing, they're here inside the sketch, and I could dimension these reference planes back to this major reference plane that's outside of the sketch, the one that divides this window into 3 sections, sections vertically. Those reference planes you can see because they're a lighter green, they're outside my extrusion. But these 2 here are inside. And I could take my pink geometry, my sketch lines, and pick the reference planes instead. So in this case, before I started drawing the pink lines, I put in the reference planes and do exactly the same thing that I did here. I'd already have these reference planes that you can see up at the top, the ones in the middle. Those would be there. So these 2 here, and these ones on the side. That one would be drawn before the extrusion, and this one as well. But inside the extrusion, I could then draw the reference planes that would be aligned with each edge of my window frame. Now, why would I do that? It would mean then that I've got these bones, if you will, inside the extrusion, and then when I finish, see, you don't see them anymore. they're not visible. So you get the advantage of using those reference planes inside the sketch to help you constrain geometry. And of course, constraining lines in the sketch, third bullet point, to reference planes contained outside the sketch, which is this example here. So those are the three different ways that your sketch lines of extrusions in particular can be constrained. Now we've talked about edge constrained, so that's using the pick tool. Align constrained, you folks also know about that. You can use the align tool, align something and then lock it. So again, an example of that would be here, let me just do the glass. So you've got two ways of getting constraints to happen. You can use the pick tool with lock, or, so here's my glass extrusion. You can see it doesn't even get quite close to the frame. I can use the align command, and I can align these sketch lines this way. It does exactly the same thing. So align constraints are the same as an edge constraint here. Same deal. Now, there is also center constraint. This is an important thing that you're going to be using when you're doing window and door frames, and I'll explain it. So it takes two dimensions to make it work. First of all, you have, and I'll just recreate these dimensions so you can see the process. So you've got your two pink sketch lines with a reference plane in the middle. So then we use the dimension command, and for the equality constraint we pick both sketch lines and also the reference plane in a single dimension. Click some white space and place it. Hold on, let me just do that again here. D-I. There we go. And then hit the EQ button after you placed it. So what this will do is it'll keep these two pink sketch lines equally spaced from the reference plane in the middle. Then the next step is to run a dimension between the two pink sketch lines and place it. And here's the thing. Once you add a label to your dimension, what Revit will do is that when you alter the value of this dimension, Revit will make sure that these two pink sketch lines stay equidistantly spaced over this reference plane that's in the middle. So that means that when the major reference planes here, these vertical guys, as they move side to side, our sketch lines will always stay equidistantly spaced from that reference plane because of this EQ dimension here. So you can see I put it on each one. Now you might decide that with your frame that you want the frame's edge to be on this reference plane. That's fine. Then you're just offsetting to one side. But if you want to keep it equidistantly spaced and centered on a reference plane, that's it there as center constraint.
Does the sequence of the dimension matter?
No. No. So you could do the dimensional parameter first and then put the EQ one on it, or you could do the EQ first and then put the dimension parameter on it. It doesn't matter which way you go. We'll talk about the constrained to a point, and this is just a dimension snapped onto a point can be used to push geometry around inside a family. Okay, so we're going to move on here, on to page 3. We're talking about solids and voids. So I'm going to close these families down here. Now, if you folks want to, I'm going to get you folks to open up a new, so go to File, New Family. Or if you're on the Revit desktop, you can just hit New. And for this instance here, I'm just going to use the generic model family template. So File, New, Family, and then choose Generic Model. So one of the things I just want you folks to understand in terms of how solids and voids interact is that the order in which they are created impacts if solids and voids interact. So let me demonstrate. What I want you folks to do is we're going to create a void extrusion here, just a circular one, and we're just going to create one of them. So there's a circular void. The default 1 foot thickness for the extrusion is fine. It's a void. So from the Create tab on the Void Forms drop-down menu, choose Void Extrusion. Just grab the circle tool out of the geometry panel and draw a circle and finish it. So voids are orange when they are not intersecting anything. So now what we're going to do is we're going to create a couple of square extrusions and make sure that the square extrusion overlaps the void that you have drawn. And finish it. And draw another one, another square extrusion, just elsewhere in the plan, and finish it. So you've got two extrusions and a void. Now you folks can see that the solid and the void is doing nothing to the solid. Now, let's create a second void. And again, I'll make it circularly shaped. So now I'm creating a void in the same geometric area as the solid, but I'm creating it after the solid. So as a result, it automatically carves geometry out of the solid in your family. So voids created first, don't cut solids created after, unless you tell them to do so. So on the Modify tab here, we've got our cut geometry commands, which tell voids to intersect solids or to not intersect solids. So here if I say uncut geometry, I can pick this void and then pick this solid, and now I've told it don't cut that solid. Or I can choose the cut geometry command and ask a solid to cut a void that is nearby. So if I have here, so just for the sake of argument here, I'm just going to copy these two solids a bit. If you have multiple solids and voids that are in the same space, you can choose whether those voids cut some of the solids or none of them. So there, that void isn't cutting any of the solids. And with the cut geometry command, I can choose which of these solids, if not both, that are being cut by the presence of this void. Once a void is cutting at least one solid inside your family, Revit hides it. It's still present. You can tab select it, so you can modify its shape, but you'll still be able to grab the void if you choose the cut geometry command again. So that's just something that we want you folks to be aware of. And of course, we do have the join geometry tool, which you folks have seen used in the context of a project. Voids and solids and voids solids and solids can interact as well. So here I've got two solids, and you can see them there, and they are, if I got a wireframe here, they're overlapping. So you got two volumes in the same place. You've got overlapping volume. If you use the join geometry command, you can merge those two solids together. Now you can see how it created that extra line here, because Revit has, as they call it, a Boolean operation. It's an additive thing there where it merges those two geometries together. You can still pull it apart, right? So here, let me just turn on shading. So here you can see, as soon as I put into that other piece, Revit remembers that you have joined those two solids together. So we'll be using solids and voids at other times during the course. With a particular solid, if you folks click on it, if you remember when we were talking about the visibility settings for solids, click on a solid and go to this dialog box. We can turn these solids on and off in particular kinds of views. So we were talking about a door leaf. So door leaves, we turn them off in plan so that you don't see them. So we uncheck that box, plan RCP for solids. Voids have no such control because they're never really meant to be seen anyway. So when you click on the void and you go to visibility settings, you know, you can change whether they're, but it doesn't make any difference. Like these voids here, once you've clicked on it, it doesn't make any difference. These voids, so they're always doing their thing, regardless of what you choose in the visibility settings dialog box. The thing is, of course, that with a void, you can see here there is no visibility parameter. With a solid, there is a visibility parameter. So this could allow you to hide certain solids in a family. And the example of that would be back in our window family here that we were looking at. You folks noticed there was like a fake header and sill underneath the window. So in this particular project, the client or the designer, project architect, wanted a fake concrete lintel and sill to be placed on top. I think it's for a tilt-up project. So we put these things on the windows, but there are some cases where we didn't want these things to appear. So when you click on these solids, and you folks can see this when you go back and look at the family. Here by the visibility parameter, you can see that there is an equals button, which means that there is a parameter which controls whether this geometry appears once the window is loaded into a project. So people can hide the head trim or the sill trim, or both, once this family is loaded into a project. So that's a visibility parameter. And when people see this parameter in a project, it's a checkbox. So of course they uncheck the parameter called head trim visible. In fact, we can see it in family types. There they are there. So if these boxes are unchecked, it means that these geometries, you can see they turned gray. Can you see that? The edges turned gray. This is what they looked like before. They were black around the edge. And then after I unchecked those boxes, the edges of the geometry turned gray. In the family and in the project, they'd just be hidden altogether. So solids have this visibility parameter that you can use to hide them. With voids, it doesn't work that way. They're just always present. So there's a note in there about the voids that you can to move. So if you have a family where you would like at some time for your voids to cut a solid in your family, and there's other times where you'd like it to not cut the solid. So let's say that there's some points where I want this circular void to stop cutting the solids. Well, there's no way that, you know, with the family that you can kind of flick the switch on that one. You can't say, yeah, please cut at some times and please don't cut at others. So there's not a, as you can see here, there's not a cut or a don't cut parameter in here. So what we do is we simply grab the geometry or the void geometry and we just move it out of the way. And so we have length parameters, dimension parameters, that will grab that void and just move it out of the way when we don't want it to cut something, and then it simply won't just because it's not there, right? So Mr. Miyagi told us that one, you know, best way to avoid solid, no be there. So by moving our voids away from our solids, that's the way that we can control whether they're present or not. In this folder for tonight, this is a structural beam family. and you folks can use this. We used it in our structure class when we were building that gazebo. So here it is. There's a little void in there, and when we don't want that void to be used, so inside the family there's these boxes here that have these check boxes. So if I don't want the voids to be notching these ends of the beam, and I hit OK, what happens is that inside this family, the voids are moved away with a length parameter, a dimension. So the dimension simply grabs those voids and moves them far enough away that they're not going to cut the ends of the beam. Okay, so we're going to move on here and talk about how you can control circular geometry and put it where you want it. Now, if you've got one of these circular extrusions, if you folks just double click on it to open up the sketch, you can control circular geometry in your families, and we'll talk about the different things that you can control. You can control where the center of the circle sits with respect to the different reference planes by simply running a dimension from a reference plane to either a quadrant of the circle or to the center of the circle. So if I first choose a quadrant, you just click on it. And why isn't it placed? Oh, I used an angular dimension, that's why. So it's using a line dimension. So pick a quadrant. So you can run the geometry to the, now you'll notice here that I'm editing a circle, so it's already existing. You have to be careful when you put dimensions in, when you're editing solids, because of this. That is not the pink sketch line that I'm hovering over. Revit is trying to snap this dimension to the edge of the solid itself, and I wish there was a kind of an easy way to explain it here. When you're trying to move sketch geometry around, you always have to make sure your dimensions are snapping to sketch. So watch when I hit the tab key and look down on the status bar down here. So that's not the sketch line, that's not the pink line. I will not be able to control where this circle sits by just running a dimension to the edge of the solid. I have to have my dimension to the sketch of the circle. So if you're not dimensioning to the pink geometry inside your family, you are not going to get predictable results. So you can't reliably, so here if I take a dimension and I run it to the side of the circle here, yes, I can make this dimension parametric, and 9 times out of 10, if I were to put a parameter on this thing, give it a label, and ask it to move the circle around, so here if I just add a parameter for it, move quadrant. So this isn't in the notes, I'm just trying to illustrate the principle here. So there's my dimension. And if I change this dimension's value, see what it did? It changed the size of the circle, it didn't just move the circle. So whereas if I go inside my family here, inside the geometry rather, and I put the dimension on here, so now if I go and change the value of this dimension in family types, oh, they did it here as well. But it's still better to see all of these controls inside your extrusion sketch, whether it's a circle or a line. So we can control where our quadrants sit using dimensions. We can also control where a circle is sitting using a dimension to the center of a circle. Now, pay attention here to how I did this. If I pick this quadrant here, if I pick the quadrant closest, it gives me a dimension from the reference plane to this quadrant. But as I pass my cursor around, look at that. See how you get the little center mark at the center of the circle? Revit's now telling you that if you click you'll get a dimension placed to the center of that circle. Now, what if I want to put a dimension from here to this quadrant? Because that's not going to move the circle sideways. If I want to run a dimension to this quadrant, I would do it from down here. So again, I don't want a dimension to the solid geometry. I hit the tab key once and make sure I'm dimensioning to the sketch. Now, the first time you guys create a circle, this wouldn't be an issue. Let me explain. So here I'm creating a new circle. So there's no solid created yet because this circle, I haven't hit finish to create an extrusion here. So notice now that when I run dimensions to this circle, it always goes to the sketch line because there is no geometry there yet. Subtle, isn't it? It's kind of the kind of stuff, you know, you feel like I didn't have enough coffee before this class, or I should have just skipped this class. I feel that. But in any event, we're trying to make sure that our dimensions go from reference planes to our quadrants on the circle. So that will allow us to control where the circle sits in space. And then, of course, we can use a radial or diameter dimension to control the sizes of the circle. And of course, we can make these dimensions parametric. So that's how we can move circles around and control their size. So this is in the one dimension looking downwards. If we want to control the height of the circles, we can do that from one of our elevation views. Now I'm just going to delete some of this other geometry here. So if we look at, say, from the front elevation, we can see our two circles from the sides, and you can see there's the one drag handle here. And so, as you folks might expect, we should put in a reference plane first, like we did for the desk a couple of weeks ago. And then we can stretch our geometry up until it hits that reference plane and lock it to it. After that, we'd put in a dimension for that reference plane so that we can control the height of this reference plane, and this geometry will stretch with it. So place that reference plane in there, give this dimension a label up here, and now we'll be able to control its size. With arcs are sticky at the corner, so if you're doing like a round topped window, here I'll do that right here. So I'm in one of my elevation views in this generic model family. So I'll just build an extrusion here, and you folks can see. So if you're doing something like a curved topped window, you can draw that arc. And so as it mentions in the notes, let's say that you have windows of varying widths, and you want to keep a constant height for the arc. So what I'm saying is, you want this arc to always be, say, 6 inches high. So as soon as you run a dimension from the reference plane at the corner of the window up to the top of the arc, this can now be given a parameter name. So that you can maintain some particular height of this arc. So even if the width of your window were to change, so if I were to give this a width parameter, it'll maintain the height of the arc. You know what I'm saying? So what's happening is that as you stretch this window and make it wider, the arc height is keeping this height of the arc the same, but of course the radius of that arc is changing. Typically when you see buildings where they do have curved tops on the windows, they want that height of the arc to remain constant along the elevation of the building, regardless of the width of the window. So the point of this is just to say that dimensioning the height of that arc, Revit will do that very predictably and with less stress. Now, we'll take a break here for 10 minutes. We're going to come back and do the assignment on page 4. We're going to be using the special face-faced window, and we'll demonstrate why after the break.